Do I need to mention it doesn't work? At the current rate, I'm going to turn this entire roll of perfectly fine yellow PLA into failed prints before getting the printer to work properly. Yes, we hit 10,000 subscribers. Thank you so much, everyone. This is a huge milestone. I'd really like to make a big fuzz out of it, as usual, but I'm still so tangled up in general life stuff with the ongoing divorce of my parents. I just don't have the energy right now. So I'm afraid there won't be a special 10,000 subscribers celebration video coming out, but I still appreciate it all the same. Anyway, I made some new parts. It's time to get my 3D printer running again. In this 17th and hopefully final part of the series, I'm going to install lead screws on the X and Y axis of the machine in order to fix my resolution issues like discussed in episode 15. I don't know yet if I'll actually get it printing again, but you'll already know since I'm sure gonna have edited that in by now if it happened. And without further ado, first step is to reinforce the top cross member, since my new filament spool holder goes on top of the printer like this, and this strip of 10mm MDF isn't exactly up to the task of supporting all that weight without bending. The filament holder gets screwed in here via some holes that mysteriously appeared right where they should be. And this is actually a pretty cool design, if I may say so myself, because totally unintended, this perfectly doubles up as a storage tray for all your tweezers, screwdrivers, and deburring tools and what have you. Now for the lead screws, I picked the straightest M5 threaded rod I could find at the hardware store. I did say I was going to try to get my hands on some coarse thread Imperial stuff so as not to bog down the maximum speed of the printer all too much, but here in the EU there is no chance. So I would have to specifically order it in, which totally defeats the purpose of being able to physically go into a store and pick out the straightest one of the bunch, and I'll for sure end up with a bent one. So M5 is the best I can do, and I'll just have to deal with the additional slowness. Of course, I could also have chosen an M6 thread, which has a pitch almost identical to a number 1024 TPI, solving that problem, but it's also thicker, with more friction in the zero backlash nut, requiring more torque from the motor, and since my steppers are really tiny and don't have much torque at all, but can spin really fast, I think I might be better off with M5. To couple the lead screw to the motor, I really need to remove this brass pinion from the shaft. Except the problem is, these are usually such a tight press fit, the only way to remove them is either by destroying them, which I don't really want to do since this is a pretty good quality gear reduction and I might want to reuse it for something else, or with a gear puller, which I don't have. And even if I had one, this pinion is so close to the motor, you couldn't even get most off-the-shelf gear pullers in there. So I made up a custom one out of some scraps with a 0.5mm spring steel blade, and it just barely fits in there. Well, that worked a treat. As a coupler to actually connect the lead screw to the motor, I'm simply going to use a piece of thin plastic tube from back in the day when plastic stems were still a thing on cotton swabs. Don't ask me why I've got a whole tub of them. Because these are actually just about a perfect press fit on a 2mm shaft, while still being flexible enough to absorb minor misalignments. Now, this is where I'm running into another issue. Because my stepper motors only have bushings instead of ball bearings, the shaft can actually be pushed in and out quite a lot. And for a lead screw, this amount of backlash is simply unacceptable. I could put a ball bearing on the other side, but even good quality ball bearings have a little bit of slack in them, so I had an idea. The motor mount gets attached to the X-axis via some oversized screw holes to allow for adjustment, and like you'd expect, the stepper lead screw assembly gets screwed to it. Then on the opposite end, I have a very similar piece of wood, except with a threaded hole instead. And here's the thing, I ground a little divot into the end of this socket head bolt and a matching but slightly steeper tip onto the lead screw, so now if I insert this bolt, I can adjust it super accurately to just put a tiny bit of preload on that lead screw, and it'll both act as a low friction bearing and push the shaft into the motor to prevent it sliding back and forth. I don't think I need to mention, this is a bad design. First, we have a mild steel on mild steel bush. It'll wear out. It's likely bad for the stepper motor to have any significant sort of preload on its shaft. And the entire thing doesn't take into account changes in humidity, lengthening and shortening the X-axis itself, so it'll need periodic readjustments to keep the right amount of preload. Ideally, the screw would need to be brass for lower friction, and importantly, it would need to be spring-loaded to exert more or less constant pressure over a range of environmental conditions. On the other hand, it seems to work fine, and I really only needed to do so for long enough that I can use the printer to print something fancier. But I still need some kind of lead screw nut to actually move the print head around, and one difficulty here is that there is not much room behind the carriage for it to go, especially since the lead screw is partially recessed into the rail. Now, quite often you'll find these so-called anti-backlash nuts, and while there are plenty of DIY designs out there, most of those are really pretty much impossible to make without a 3D printer, so I settled on the easiest solution possible, cutting the thread into a piece of material using the threaded rod itself as a tap, so the resulting nuts fit super snugly and there virtually is no backlash. And of course, the nut would ideally be made from plastic rather than wood because of the lower friction, so I thought I'd get real fancy and try to injection mold the part using the printer hot end as a miniature injection molding machine, which would also make producing plenty of these parts as a replacement once they get worn out really easy. So I spent a couple hours making a mold that can be disassembled and tried it, and of course it didn't work. The filament cooled down way too quickly and never even came close to filling the mold. In hindsight, I could really have used my head and figured that was bound to happen, but oh well. To fix this, I would at the very least have to preheat the mold, which I didn't feel comfortable doing given it was all wood. So instead of wasting any more time on it, I went ahead and made the dang nut out of the, to my knowledge, hardest wood I own. This is briarwood. When I was a teenager, we once met a professional pipe maker and he gave me some of his scraps. That's how I got it. I always held onto this stuff for something special, and here we are. I made 2 nuts. For convenience, the exact same design, just different lengths for X and Y. And these fit my old thread really accurately. As far as wear resistance goes, I have no idea how it stacks up against plastic, PTG more specifically according to my TechFun's recent test, but my bandsaw has beechwood guide blocks and they've been holding up surprisingly well. In fact, this is still the first set I ever made for that saw when I built it back in 2018. Yeah, they're about done now, but in that time I've also worn through 2 ball bearings. Now, because this is still wood and lead screws need to be greased, I somehow need to seal up that nut against the grease. Otherwise, capillary action will suck it away and the stuff will permeate the entire nut, maybe even propagate into the X carriage. Oil and wood is never a good combo. So I'm going to use exactly that to my advantage and soak the nut in molten paraffin wax, which will hopefully plug the pores and prevent the grease from entering. That's certainly the first time I've deep-fried wood, albeit unintentionally, though I'm pretty sure that's what basically just happened. And this is the point where I need to wind the carriage back and forth to adjust the end plates in order to have the whole thing run as friction-free as possible. Alright, I ended up greasing it as well, and it seems to run mostly smooth now. Getting everything to align properly was surprisingly easy by basically loosening the motor mount, driving the carriage all the way to the end, and retightening it, which basically puts the lead screw where it naturally wants to sit, being constrained by the lead screw nut on the carriage. Of course, do that on the other side as well, and now the lead screw should theoretically be mostly parallel to the rails. Anyway, now I need to do the same to the y-axis, and I'll do that off camera since it'll be the exact same process, except way faster without you tagging along. And while that happens, let me tell you about PCBWay. Now, building electronics is fun, but whenever we build our prototypes on perf board, they usually either don't work or emit magic smoke upon being powered up. Fortunately, we live in 2024, and it's actually really easy to design even complex PCBs in CAD and get them professionally made by PCBWay. Just select your preferred silkscreen color and a few other specifics, upload the Gerber files, and bam! As little as a few days later, high-quality printed circuit boards turn up on your doorstep. And even better, if you're designing a product and don't want to manually solder hundreds of boards, PCBWay will do it for you, as well as manufacture any imaginable 3D printed, laser cut, CNC milled, or even injection molded parts you might want. So if you're in need of PCBs or any of those manufacturing services, go to PCBWay.com or click the link in the description, because supporting the sponsor ultimately helps out the channel. And big thanks to PCBWay for continually supporting tiny channels like this one. And wouldn't you know it, the y-axis is complete. As you can see, it's pretty much the exact same thing, with the stepper motor being adjustable at the back and a botched-in piece of plywood at the front. The only change I did was to actually use a brass screw for lower friction, the head of which is hidden away in this hole here, which is actually a good thing because it means you can't accidentally bump it like the one on the x-axis. I might still end up replacing this one in the end. I did end up moving the stretcher bar from up here to down there, so it's now fully attached to those cross members, and the spacing between the nut and the carriage didn't quite work out from CAD to reality, so I put a little plywood spacer in there, but other than that, it's the exact same as the x-axis. But I'm sure you want to see it move under its own power, so let's try that next. Right, I hooked it up to my usual setup for controlling stepper motors with a potentiometer, so we'll see how fast I can make it go. In theory, based on the 200 millimeters per second it was previously able to go with the direct drive, I calculated it should now get up to 30 millimeters per second, because with this gear reduction, the motor needed to spin at 2400 RPM to move the carriage at 200 millimeters per second, which works out to 32 millimeters per second with a higher speed reduction by the old thread. Of course, how much of that it'll actually reach depends on the amount of torque required to turn the lead screw, so I don't expect it to go anywhere near that fast, considering this tiny brass pinion presented barely any load for the motor compared to whatever this is. Anyway, here goes nothing. This looks like the maximum speed I'm getting before it stalls. And I'm not even going to pretend to be surprised here because curiosity got the better of me and I did do some testing off camera. But yeah, to my eyes this looks like about 20 millimeters per second as a rough estimate. We'll know for sure once I finish the Marlin setup. The threaded rod does seem to have a rough spot right around here though. It makes a weird noise every time it passes. Anyway, let's try the y-axis. Yeah, it's pretty much the same. Notice how much quieter it is though. Like, unless the motors are going really slow, which I don't think they ever will given how slow the entire thing is, it just makes a whirring noise instead of rattling and chugging along like it previously did. It's also kind of insane how fast the lead screw needs to spin to move the carriage at that speed. Just listen. So yeah, I would call that a success. Now I just need to put everything back together and try printing. I didn't finish the cable management, so this is still pretty temporary because what I need to do now is to actually get it printing in order to print some replacement parts, like actual spring-loaded anti-backlash nuts and some proper pulleys to replace the wooden ones on the Z-axis. But to install those, I have to take the whole thing apart again anyways, so there's no point finishing up the wiring just yet. Speaking of lead screw nuts, my fancy deep-fried wooden ones unfortunately didn't eliminate backlash entirely. Now that it's worn in from playing about a little bit, I can tell there is over 0.1 millimeters of slack in either axis, so I'll have to take that out using backlash compensation until I can get the right size of brass threaded inserts ordered and 3D print proper spring-loaded ones to eliminate it entirely. That said, I now have to get all the software stuff set up and tuned again and do some test prints. That'll happen in, for you, an instant. And finished. Would you believe me if I told you that this printer can print at a top speed of not 10, not even 20, but 32 millimeters per second? Yep, my math was right and my estimate wrong. I can actually run it at the advertised max speed, which is pretty good as far as lead screw based systems go. Now, I did encounter my fair share of weird issues, so it's currently running a little bit slower at just 30mm per second tops, because on a few of my calibration cubes, I got a suspicious layer shift in the y-axis at around about the same layer height every time. Turns out, after the machine's been running for a while, the lead screws mysteriously develop too much preload, which causes additional friction in the bushings, and the motors start skipping steps with particularly hard accelerations. Of course, this happens predominantly on the y-axis, seeing as the print bed isn't exactly light. I haven't yet figured out if it's the threaded rod expanding from friction-related heat, which is unlikely, or even the entire frame of the printer shrinking from being dried out by the heat of the print bed, which is even more unlikely because the print bed is not a hot plate and doesn't emanate that much heat, or maybe even something inside the stepper motors expanding. After all, they do get quite toasty in use. I'm also still experiencing quite a few random blobs and stringing, and sharp corners always end up bulging a bit. Despite the extruder now being direct drive, it just doesn't seem to have enough fine control over the filament. I don't know if it's a limitation of the 28BYJ not being able to retract fast enough, or maybe it could easily be fixed using linear advance. I'm really not good at tuning 3D printers and quite stressed about finishing this video at this point, so I admittedly really only did the basic stuff to get it working well enough, if you know what I mean. This might also not be a very friendly model to show off any printer with. It has single perimeter walls and steep overhangs, and 2 layers of solid infill to close off the top just ain't enough. Well, I guess if I compare before and after my upgrades, there is a lot of improvement. This is with a lot of manual cleanup and patching. This is straight from the print bed. Yeah, I guess it prints well enough for now, so let's print this anti-backlash nut I designed for the y-axis. As you can see, it has a spring already built into its shape, so I don't need any hardware aside from the nuts. Of course, using regular mild steel nuts is not recommended, but like I said, I currently don't have any threaded inserts, so this will have to do for now. Also, while we're talking about Backlash, it might be worth mentioning I didn't activate Backlash compensation after all. I mean, I tested it, but quickly realized that unless it's really well configured, it tends to induce layer shift, and I've really had enough of that on this printer, so because the results ultimately didn't look any better than without, I just turned it off again. So yeah, this is literally printing with over 0.1mm of backlash in both axes, and the result just looks a bit like Z-banding. It really doesn't seem to have much impact on actual print quality. I really wish I'd have had enough time to spend a week properly tuning this printer before showing it off, but never mind, I guess. Now that it's cleaned up and assembled, you can see the way it works is by squeezing it a little bit to add some spring tension before the screw engages with the second nut. And now, theoretically, we have zero backlash. And here it is installed. Of course, this comes with a trade-off. Because my stepper motors have basically no spare torque at all if I want to go fast, adding additional friction to the lead screw by spring-loading the nuts means I cannot go 32 millimeters per second anymore. If I now try to move it at the previous maximum speed, it just stalls. I have to decrease the feed rate to 80% or about 25 millimeters per second to still reliably get motion. On the bright side though, if I now turn the lead screw, every 100th of a millimeter is accounted for, and just look at that repeatability. Let's see if any of the Z-banding in the Y-axis, does that even make sense? I mean, the backlash artifacts in the Y-axis. Let's see if those disappeared. Do I need to mention it doesn't work? Obviously, steel on steel friction is too much. Just listen to the horrible scraping sound it makes. But why the frick does the X-axis stall as well? And why for the love of God does it not slow down when I lower the feed rate? Anyway, with that unexpected end to this little excursion, let's put the wooden lead screw nut back in, get it working again, and try printing something that actually works. Not gonna lie, at the current rate I'm going to turn this entire roll of perfectly fine yellow PLA into failed prints before getting the printer to work properly. Thank goodness we're back. Apparently this wasn't as good an idea as I hoped. Who would have thought wood outperformed steel and plastic, huh? I think I know what went wrong earlier. While lowering the maximum feed rate in Marlin, I somehow messed up my acceleration settings. Those were way too high, and so of course the motors couldn't keep up even at lower speeds. For this second attempt, I'm just carefully cutting the threads directly into the plastic, and then I can pinch in this tab with an additional screw to hopefully take out any plate. Here on the bench it seems to work just fine. Let's see if it still does so on the printer. Well, believe it or not, it actually does. And it doesn't even sound horrible. Now, I did have to reduce the speed again. It is more snug than the worn wooden nut after all. As far as Backlash goes, it's obviously not as good as the spring-loaded one. I can feel sometimes there is a tiny delay between when I start turning the lead screw and the dial indicator actually registering motion. But that should be in the hundredths rather than tenths, so I'm hopeful this time we'll see a dramatic increase in print quality. Honestly, I can't really see any appreciable difference. This is the X-axis with Backlash, and this is Y, supposedly, without. I'm starting to think the extruder might just not be up to snuff for producing good quality prints. Which is hardly surprising, seeing as it rocks the cheapest stepper motor in existence. Just for completeness sake though, let's print a very similar but slightly smaller anti-backlash nut for the X-axis. Well, that's it installed now. Runs nicely enough. I guess Backlash should be a thing of the past now. At least I can't feel any. Last but not least, I think I'm not the only one who wants to see a proper benchy, one that doesn't look like a pug the way the pre-upgrade one did. I am a little anxious about it taking 3 hours to complete, seeing as each of these test cubes took over half an hour to print and is only a quarter the amount of filament a benchy uses, but let's try it anyway. For this, I'm going to open a brand new roll of red PLA, just in case the yellow one was stringing more than usual due to being wet. I think at this point I've definitely spent more on filament than on the printer already. And even though this printer has so far not exactly been easy to use, filament changes are a breeze. Well, it's not the greatest benchy I've ever seen. If this was from any other printer than a $50 one built out of trash, I would probably not be too happy. There's still a lot of inconsistent extrusion, and the oozing just ruins all the seams, even if we ignore all the stringing. There's also some weird ringing that I don't know where it comes from, seeing as there isn't any on the other side, if the camera may focus. So yeah, but compared to before the upgrades, well, it's worlds better, I don't need to tell you that. This is after cleaning up a lot of stringing, and this is straight off the print bed, so there is a giant improvement still. To put that into even better perspective, this is my very first print. Yeah, we've come a long way. And that benchy only took 2.5 hours to print and 3 failed attempts to get right. If there's one thing this printer is not, that would be reliable. So, this is what I'm officially going to call the end of this video series. Obviously, there's still a long ways to go if I want to get this machine to spit out really good quality parts, but any further upgrades will not be free. So I think this is about as far as I can go with my initial $50 claim. I really need to replace the extruder to get rid of the inconsistent extrusion, and also because I think the backlash in the gearing of the 28BYJ might be to blame for all the oozing. I don't know how much of that could be tuned away, but it's probably not worth trying. I also need to replace my inventive conical bushings with good quality ball bearings, even though they show barely any signs of wear yet, because the entire printer constantly reacts to humidity and temperature, and so this bushing was adjusted to be snug when the machine was hot, but now that it's cooled down, there's like 0.5 millimeter of play. That's the biggest problem I still have right now, because I would adjust the bushing while the printer is cold and then start printing, at which point it heats up and the lead screw basically becomes too long and builds up a lot of tension, which ultimately makes the motor stall and you get a benchy like this. It just makes for a very frustrating experience if I have to let it run in for like 4 hours prior, producing failed prints until everything's finally warmed up enough it stops moving. If all early 3D printers were like this, by God, I don't know how anyone had the patience to even try to make it work, instead of just saying,
"That newfangled 3D printing ain't never gonna work."
But at this point it's basically history. The printer does produce totally usable parts, even though they still require a little bit of post-processing, so you'll see the printer change and improve in the background of other videos. A huge thank you to everyone watching, liking, subscribing, and commenting with great suggestions. I totally stumbled into this, but the RepRap community is really awesome. Special thank you to all the super kind folks supporting these shenanigans on Patreon. I really hope you enjoyed, and I'll see you next time. Bye bye!